last part, we're going to look at what's called the greatest integer function. And the greatest integer function, you see it a lot in computer programming courses. It's also known as, in computer programming functions, the floor function. And in computer programming classes, usually looks like this around an X. However, in math courses, we call it the greatest integer function. And what you'll notice is the greatest integer function has two brackets on either side of your X. And what this greatest integer function is it rounds down any decimal value to the nearest integer. So for example, what this means is if we take the greatest integer function of, let's say, 0.2, it rounds it down to the lowest integer, or the integer less than or equal to this, which is 0. So also, let's say we had the greatest integer function of, let's say, even 0.8. It does not matter that it's a 0.8. That technically it's closer to 1. It always rounds it to the greatest integer less than or equal to the value. Well, the greatest integer that's less than or equal to that value is actually 0, so it rounds it down. So that's going to be actually equal to 0. And that's why I like, actually, instead of calling it the greatest integer function, I like calling it the floor function, because that reminds me of rounding it down. The floor is below you, so you're always going down no matter what. So even if you had, let's say, the greatest integer function of 1.999, it's going to get rounded down using the floor idea to 1. However, if you take the greatest integer function of an integer, 2, it stays exactly where it is. It stays at 2. So let's take a look at an example of these. Well, if we look at this one that's over here to the left, it's the greatest integer function of just x. It has not been shifted. And what you'll notice is the function itself looks like it's a bunch of pieces. That's why we talked about piecewise functions first in this section. And these pieces look like steps. So a lot of times in computer programming, we'll call these step functions. Why? Because they look like a bunch of steps. And on one side, you'll have a closed circle, and on one side, you'll have an open circle. And the idea is, here you've got your whole number 0, so 0 stays at 0. Anything in the middle, like 0.2, will round down to 0. 0.5 will round down to 0. 0.9 will even round down to 0. But hey, the reason why at 1 here, there's an open circle is because 1 is going to stay as a value of 1. That's why it has the closed circle up here. Then 1 point anything, which is over here, stays at 1 and gets rounded down. That's what the greatest integer function is. But when we get to 2, here, again, there's an open circle because 2 will stay as 2, and that starts our next step. So now what we want to do is just some basic examples of these step functions, nothing crazy. So look at this first one, f of x equals the greatest integer function of x plus 2. Now we know that because there is this plus 2, and it's on the inside, it should be doing the reverse of what we think, which means it should be shifting it to the left 2. So it should take the graph that is up top here and shift it to the left 2. Now, I wouldn't necessarily trust that. What I would do is just go ahead and start plugging in some values. But the idea with our step functions is that we need to make sure that we're plugging in decimals, because that's what's going to vary from piece to piece, is what's happening with our decimals, not really what's happening with our whole numbers. So let's plug in a few values. Let's start out with, let's say, 0, 0.5, and then let's plug in 1, 1.5, let's plug in 2 and 2.5, just so that we get an idea of what the steps look like and kind of the pattern. Well, let's see what happens. If we plug in 0, we'll get 0 plus 2 into our greatest integer function, which will get us the greatest integer of 0 plus 2, which is 2. Well, 2, it's an integer, so it'll stay as 2. The next one will have 0.5 plus 2, which will give us 2.5. Well, the greatest integer function of 2.5, remember, it always rounds down. Think of it as a floor. So if it's 2.5, it'll get rounded down to 2. So let's just plot one more. So let's do 1, and then we'll plug that into our function. 1 plus 2 gives us 3. Remember, the integers stay the same, so if it was 3, it's going to stay as 3. So let's go ahead and plot this, at least to start. So at 0, we're actually at 2. So let's do a closed circle of 0 at 2. And then even at 0.5, we're up to 2. But at 1, we jump up to 3. So that should be where our first step stops. So up till 1, we've got that we're on our first step, and then after that we're jumping up to at 1 to our second step. Okay, keep on going. What happens if we plug in 1.5 plus 2? We get 3.5. Well, again, it's the floor function, so it's going to round it down, so 3.5 will round down to 3. So we're still in the same step, and then if we plug in 2, we get 2 plus 2, which is 4. That's an integer. It's going to stay where it is. So greatest integer function of 4 will stay at 4. So here what we've got is our first step switches. You can tell here at, or second step here switches at a value of 2 goes up to 4. So that means our previous step ended there, so I should put an open circle, and you can kind of start seeing the pattern here. So I can go ahead and fill in the pattern. We get what's going on. And make sure that it continues on forever so that we are making sure, even though they are steps, just like most functions, unless they tell us it will stop somewhere, it does continue on forever. So if you wanted to kind of indicate that, you'll see this sometimes where you do a ... to let you know that those steps are going to keep on going forever. Now on our test, because they're in my math lab, there is no way to actually have you graph these, so these will be multiple choice questions most likely. On a face-to-face class, I would give these as a blank graph. They'd have you graph though. In this next one, we're going to look at the greatest integer function plus 2. And we've done things like this before. Because the plus 2 is on the outside, it means our function should be going up to. So we should have kind of the same thing going on with our steps. It just should be a plus 2. So what we'll start out with is, again, the same idea, doing a table of values, because we're not going to trust ourselves to just go ahead and shift. So we'll do the greatest integer function plus 2. So we'll start by plugging in some very similar values that we did to the last one. So we'll start by plugging in, let's say 0. Well, if you plug in greatest integer function of 0 plus 2, you'll get, well, greatest integer function of 0 is 0, plus 2 is 2. So at 0, you would have 2 again. And then plug in, let's see, 0.5. We'd have the greatest integer function of 0.5 plus 2. Well, notice 0.5. Greatest integer function would go down to a 0, plus the 2 would still be at 2. Plugging in 1, greatest integer function of 1 plus 2 would be, well, greatest integer function of 1 is 1, plus 2 is 3. So at 1, we'd be up at 3 at the next step. So that means our previous step ended there and swapped right there. And we can start to see a pattern again already, but if you're not sure, keep plugging in values. We'd plug in 1.5, and we'd get the greatest integer function of 1.5 plus 2. Well, 1.5 would round down to 1, plus the 2 would still give us another 3. Plugging in 2, greatest integer function of 2 plus 2 would give us, well, the 2 would stay the same, plus 2 more would get us 4, which means the next step would actually start at 2, 4. And it means also the previous step would have ended at that value as well. So then we get our steps that we can start filling in. You see a pattern that's forming. We can just start filling in the rest of the steps. And again, I would fill it in for a while just so that we make sure that we've got the pattern right. If you need to plug in more values, you can. And then we've got our dot, dot, dot showing that it goes on forever. So notice that this graph looks pretty much identical to the last one, even though we were shifting up, not left or right. So that's pretty interesting, isn't it? However, let's try one last one with the floor ceiling function. Let's try this last one more. So let's work on this one. We've got the greatest integer function of 0.5. So this is going to have to do with stretching. So we may have to be a little bit more creative than we would have with what points we select, but it's still the same idea, is that our function is the greatest integer function that gets multiplied by a half inside. So let's see what that's going to do. So let's plug in a few more values that are decimals just to get an idea. So plugging in 0. Well, 0 times the 0.5 inside would still give you 0, which will stay as 0. Let's see, plugging in 0.5 or half. Well, 0.5 times 0.5 and half would actually give us 0.25, which would stay at 0 as well. Then if we plug in 1, we get 1 times 0.5, which is 0.5, which will still stay as 0. 1.5, let's see, if we plug in 1.5 times 0.5, that will get us 0.75, which is again still 0. Plugging in 2. 2 times a half will finally get us 1. Greatest integer function of 1 is 1. So that's where we would start our new step. So that means at 0, we have 0. Zooming in, let's say when we have 0, we'd be at 0 on that first step. We'd still be on that first step at 0 at 1, which is not how it's been so far. But we'd switch to our new step here at 2. At 2, when we get out 1, this would be our new step. So, zooming in, we would get, at 2, we'd be at 1. That'd be our new step. So our previous step would have stopped below that. And if you want to get a continuation of what this would continue to look like, you could do more values. Plug in, now that you kind of have an idea of what's going on, plug in, let's say, 3. If you plug in 3 times a half, you get 1.5, which still, again, will round down to 1. Plugging in 4 times a half will finally get you up to 2, which will stay as 2. So you will not switch to your third step until you hit here at 4, 2. So, zooming in, we would be at 4. We'd be up here at 2, which means the previous step would have ended right below it. And now we're starting to see what our pattern is. And we can kind of mock it and continue. But what we're noticing, and I'll fill in my dot, dot, dots here, is that our steps are stretched out. Our steps are actually longer. It's still the same picture in about the same spot, which makes sense if you think about how functions work. When you're doing something to the x values, which it looks like we're doing something by cutting it in half, but remember with x values it actually does the reverse. So instead of cutting it in half, it actually does the reverse. It doubles it. So it's doubling the size of the stairs. Had the factor that we're multiplying been on the outside, it would have done exactly what we would have expected, but because it's inside with the x's, we actually do the opposite. It's a little strange, but that's how it works.